Good. Welcome, everybody. It's a great pleasure to have you here today, Florian. Florian is currently an Ordita assistant professor in Stockholm, where he moved in 2020. He got his PhD at the Arnold Sommerfeld Center in Munich, studying theoretical and phenomenological aspects of extra-dimensional models. Then he moved to the University of Nottingham for his first postdoc, and to the University of Southern Denmark, CP3 Origins, for the second one. During that time, he started working on early time modifications in lambda quarter matter and dark energy model building. And today he will present addressing cosmic tension with a new phase transition in the early universe. Florian, when you're ready, you can start, please.
Thank you, Eleonora. So let me first say that I'm very happy and excited to give a talk as part of this very nice seminar series. And what I want to do today, I want to try to convince you that a new type of phase transition that occurs in the dark sector of the universe before recombination is actually an interesting scenario to think about and address the cosmic tensions, in particular the Hubble tension. So this is work done in collaboration with Juan Cruz and Martin Slot, both from Universe Origins at the University of Southern Denmark. So I want to start my talk by giving you an overview of the project. So the main motivation is provided by the Hubble tension. And I will argue that the Hubble tension should compel us to modify lambda CDM at early times. So this doesn't mean we modify it only at early times, but it's more like a necessary condition. There can be also late time component, and in fact, I will argue for such a late time component also later. And well, this idea of modifying lambda CDM at early times will bring us to the model of new early dark energy, which is motivated by the phenomenological success of the early dark energy model you might be familiar with. And at this point, my talk is going to split into two tracks. On one side, I'm going to talk about the microphysics of new early dark energy and introduce the idea of having a phase transition in the dark sector, a vacuum phase transition described in terms of a two-field model. And that phase transition is going to take place around the EV scale, which is the energy scale around matter radiation equality. But on the other side, I will talk about a phenomenological description of that model. And the reason is that the microphysics and EV scale microphysics really takes place on very short length scales. I mean, the EV scale corresponds to the micrometer scale. So to really test such a model against cosmological data, we need to come up with a coarse-grained description valid on much larger scales. And that we are going to achieve in terms of fluid models. And this is also what we have done. I mean, in terms of the fluid model, we think about the trigger decay of a new type, a new phase of dark energy, early dark energy. And this is also the model we implemented in Boltzmann code, and we can test against data. So I will talk about both the microphysical models in terms of Lagrangians and a phenomenological fluid model. And a lot of our past and current work goes into establishing the dictionary between both sides, the microphysical and the phenomenological side. But of course, as I said, having the fluid model is important because it allows us to test the model against cosmological data. And the idea behind it is, and of course, that this can inform the microscopic model building and vice versa. And this back and forth between both sides, I'm going to exemplify in this talk in terms of the trigger component we have in this model. And this is really also the crucial difference with the previous early dark energy model you might be more familiar with. So the argument is that cosmological data is going to compel us to have a very quick phase transition. And I will argue in my talk that this can be achieved in terms of a trigger field. But then, interestingly, this trigger field can also help us with another problem we have with data, which is the S8 or large-scale structure attention. And if there is time, I will also hint at how this trigger field might also help us with other particle physics challenges we have. So I think the message I want to convey with this picture is that we consider this new early dark energy a vast playground to explore the microphysics of the dark sector in terms of a phase transition around the time shortly before recombination. But these things are not set in stone. I mean, this is really work in progress, and we are trying different things, and so I can provide you with a snapshot of what we are currently doing. So let's get started. So first, I want to make the case for early time modification of the expansion history, and given the audience here, I think I can make that very short. I think for that, it's instructive to look at this plot by Knox and Milea, which is already a couple of years old, but it contains, of course, the important information. First of all, there's the Hubble tension, which is the discrepancy between the Schu's inferred value of H naught and the CMB inferred value, typically by the Planck experiment, which is indicated as this tiny blue ellipse here in the center. And you see by eye that this orange band corresponding to Schu's and the CMB measurement are discrepant. And by now we know this discrepancy has risen above the 5 sigma level. But there's more information in this plot, because there's also this green tilted band, which you obtain in a fairly model independent way when you combine BAO and supernovae data. And doing that actually constrains the product of H naught times the sound horizon. The sound horizon characterizes oscillations in the primordial fluid. So this tells us that in order to raise H naught, a necessary condition is to also lower the sound horizon. But as I said before, this doesn't mean that this is all we need to do. I mean, there might be additional elements, also late time elements to that story. But in any case, if you plug in numbers, what you find is that resolving the tension requires you to lower the sound horizon by 5 to 6%. And if you look at the definition of the sound horizon, it tells you that you can only achieve this in a finite redshift window between recombination, which is the lower limit of this integration, and a redshift of maybe 25,000. And the reason is that the sound horizon is inversely proportional to Hubble. So Hubble acts like a cutoff in that integral. And that is, I think, very exciting news, because it means that that the new physics we are going to postulate falls entirely within the CMB epoch. So whatever we do, it's going to be highly constrained. And that is, of course, a very interesting situation from a model building perspective. And of course, this is not a new insight, and you could say this is a road well traveled. And what you typically do if you want to lower the sound horizon, I mean, there are different ways of doing it, but the obvious one is to, and that's the one I'm going to focus on in this talk, is to have an energy injection. And so if you parameterize Hubble in terms of the energy budget, so you have omega lambda, omega radiation, omega matter, and then you introduce a new component, which I call omega x. And that new component leads to an increase in Hubble. And if you make it relevant before recombination, it's able to lower the sound horizon. And you need, if it happens around matter radiation equality, you need something like 10% of the energy budget. So quite sizable, actually. And of course, the challenge here is to preserve the fit to CMB, because as I said, I mean, you are entirely within the CMB epoch, meaning that modes we observe in the CMB have entered the horizon during that time. And the canonical example here would, of course, be dark radiation. And if you look at simple implementations of dark radiation, where you just free up the number of neutrinos, say, then you run into problems because you get too much diffusion damping in the CMP on small scales. So I'm going to talk about that later on in a little bit more detail. So this is a very general observation you have within these models. And in the case of dark radiation, you just lack the freedom to compensate that enhanced damping. But I think it's also fair to say that there are more kind of elaborate proposals like the Myron proposal or the STEP proposal, which look more promising. But this is again not the direction I'm going to take here. And instead, I will look at a different class of models that also have proven to be quite successful phenomenologically. And those are of the early dark energy type. And I mean, the important work here in the context of the Hubble tension was, of course, the paper from 2018 by Poulin, Smith, Kowal, and Kamionkowski. And they showed that within a particular scalar field model, they were able to address the Hubble tension. But to give you an idea of what's going on in these models, I think it's instructive to look at this plot, which shows the expansion history of the universe in terms of the relative energy budget. So you, of course, you start out with radiation domination here in orange, then eventually matter here in blue takes over. And well, if you for a moment forget about this blip down here, then at late times, dark energy here in red is going to take over, and you're left with the energy budget today. As we know, it's some 70% dark energy, 26% dark matter, and 5% ordinary matter. But now the idea of these early dark energy models is to have an energy injection, as I said, around matter radiation equality, so indicated by this dotted line here. And why do we call it dark energy? Well, because it rises like a fluid with an equation of state of -1. It doesn't have to be perfectly -1, but -1 gives you the steepest possible rise. And then it decays afterwards. And phenomenology tells us that this decay works best if it's somewhat stiffer than radiation. So particularly well works an equation of state of around 2/3. And I mean, this idea of having this type of energy injection is valid for different types of early dark energy models, in particular also for the new early dark energy models. So in fact, what I plotted here is actually already within the new early dark energy model. So in the old EDE model, this would be more like a smoothed out peak, but the idea is the same. So as I said, this energy injection then lowers the sound horizon, which is compensated by increasing H0. And this was also the starting point of my work together with Martin Slot, because we realized that, well, this energy injection looks very much like a vacuum phase transition. So what is a vacuum phase transition? So let's first look at the single field case, because here things are very simple. Imagine you have a scalar field with a non-trivial potential. And the potential has two minima, a false minimum and a true minimum. And initially you prepare the state such that the scalar field resides in the false minimum. And then the idea is that the corresponding potential energy provides early dark energy. Because it's potential energy, it has an equation of state of -1, which exactly gives you this steepest possible rise in this plot I showed you before. But then eventually this field is going to tunnel to the true minimum. So this is the analog of the quantum mechanical sub-barrier tunneling, just generalized to quantum field theory. And what it means in position space is that you nucleate bubbles of true vacuum. So this I show here. So the point is that the field inside this bubble is already sitting in the true minimum. indicated by the green color, but outside the bubble, you are still in the false vacuum. And there's an interpolating region, which we call the bubble wall. And once these bubbles come into existence, they very quickly start to expand, and they expand almost instantaneously with the speed of light. They accelerate very quickly. And eventually they start to collide. But this very simple idea faces an obvious problem, because if you just write down a model with such a potential, you will find that the tunneling rate is constant, because there is no particular time dependence in the problem. And this means that at early times, and when the Hubble parameter is much larger than the tunneling rate, tunneling is not efficient. And the reason is simple, because the expansion of space outruns the probability of creating bubbles. So the space in between bubbles expands too quickly, and you cannot fill all of space. Percolation is not efficient. But once Hubble drops, eventually it's going to be of order of this tunneling rate, and then suddenly tunneling can keep up. But the problem is that this percolation is going to be very slow. It's a one-scale problem. Everything is going to be set by Hubble at that time. And you will find that typical bubble sizes are also of order of the Hubble lengths. And the reason being that they expand almost with the speed of light. And then, of course, you are faced with a problem, because, as I said before, this happens during the CMB epoch. So you suddenly introduce a source in the cosmic fluid that is active during, or in the dark sector still, but it's active during the CMB epoch. And you create these bubbles which correspond to a density contrast of roughly 10%. And this will create large anisotropies in the CMB. So simply speaking, you should be able to see the bubbles in the sky. And that we, of course, don't do. I mean, we know the CMB is highly isotropic. So we need to find a way of avoiding that problem. And that was the starting point of this new early dark energy, because we realized we somehow need to make that tunneling rate time dependent. And that brings me to one particular implementation of that idea, which we call cold new early dark energy. Here we introduce a trigger field, an additional scalar field, to synchronize that decay. This model is really a low energy adaptation of a model that has been proposed in an inflationary context. In fact, in the context of old inflation, as a way to avoid the graceful and exit and big bubble problems. And it was proposed by Andre Linde and Kati Frese and Adams in the early 90s. And well, to get an idea of how this model works, I think it's useful to look at this sketch of the potential here on the right. So initially, the field is frozen high up in this valley, and it cannot tunnel to the true minimum, which is indicated by this white dot, because there's a huge potential barrier. So the tunneling rate is highly suppressed. But eventually, the field drops out of slow roll as the Hubble friction is released, and the field starts rolling down this valley. And then this tunneling direction opens up, and eventually you turn on this tunneling rate. And what is important is that the tunneling rate now becomes a time dependent, because it's dependent on this trigger field, and the trigger field itself, of course, has a time dependent. So we can turn on the tunneling, and it can happen very abruptly. So if you write down a model, and you can, the simplest model I think you can write down is a quartic model in the tunneling field psi and quadratic in the trigger field phi. Then you realize that you need two very different scales in that model. So there's the scale capital M, which is the scale that sets the scale of the tunneling. So as I said, it's the EV scale, because that's the energy scale of the cosmic fluid around matter radiation equality. But then there's also the trigger field, and we want it to be released at the right time. So it has to be much lighter, 10 to the minus 27, because that's Hubble around that time. So, but this hierarchy of scales you have in that potential is actually useful, because it means that, well, you start out with a tunneling rate that is exponentially suppressed, but then you end up with a maximal tunneling rate, which would correspond to this red dot, which is much higher than the Hubble parameter, exactly due to this hierarchy of scales. So it's many orders of magnitude larger. So in other words, as the field runs down this potential, it scans many orders of magnitude in the tunneling rate. So you make the tunneling very rapid because you turn it on so quickly. And that's the important point. So it happens on a very short scale compared to cosmological timescales. So to repeat, I mean, the central requirement in this model is that the percolation time, I call TB here, so the time it takes to convert all of space to the true vacuum, is much shorter than the Hubble time at that time. And nicely enough, I mean, there was a paper, I think beginning last week, where the authors looked in more detail at the bound we need to satisfy in that case, and they found that the percolation time has to satisfy that bound. And exactly in our model, due to the presence of the trigger field, we can easily satisfy. And as a consequence, the phase transition is an almost instantaneous process on cosmological scales. So that's the picture. You start in the false vacuum, then the trigger field starts to roll down this valley of false vacua, and eventually this tunneling opens up. And the tunneling rate shoots up, and then you populate almost instantaneously all of space with the bubbles of true vacuum. And the important point now is that they don't have time to grow big. They remain small and start to collide, and you're left with a condensate of colliding bubble walls. And if you want to get an idea of how this could look in a numerical simulation, this is one taken from a paper that looks at the thick wall, so-called thick wall limit of vacuum nucleation. So you indeed see that after the nucleation, you can still recognize the bubbles, but then after a little while, they start to expand and collide, and then you are left with a very complicated state of these bubble wall fragments. But the important point here, and I should say the state of bubble wall fragments, it corresponds to small scale anisotropic stress, where the small scale is really set by the size of the bubbles when they collide. And due to our percolation condition, this can be a microscopically small scale, much smaller than cosmic scales at that time. And of course, now the point is that if we zoom out and looking at this plot, there is no preferred direction or position in the problem, so we can describe it as an ideal fluid. But it still has a very rich phenomenology, because anisotropic stress is going to source a shear in the gravitational sector, tensor shear. And that's something you're familiar with, because as you know, first order phase transitions source gravitational waves. So you get something that behaves like radiation, but you're also going to source vector shear and scalar shear. And in particular, vector shear is interesting because if you look at its effective energy density, when you average or when you coarse grain, then you find that it has an equation of state of 1, so it behaves like a stiff fluid. But this is complicated physics, and we are currently in the process of working out the different ratios between these different components. But of course, if we want to see if such an idea of a phase transition has any merit phenomenologically, we can still make progress by writing down a phenomenological model that attempts to capture the physics of what I just described. And that brings me to the phenomenological NEDE model, which introduces a fluid which initially just plays the role of a cosmological constant. So this is the phase where the field sits in the false minimum. And so what I plot here is, again, the energy budget of the universe as a function of scale factor. And again, orange is radiation, blue is matter. And around matter radiation equality, you see this phase transition indicated as the dotted line happens. And initially, new early dark energy is just a constant, but then it decays. And this decaying phase we describe as a fluid that is described by an equation of state. And in principle, that equation of state is going to be time dependent, and it's going to depend in a quite non-trivial way on the parameters in your microscopic potential. But for now, we take it as a phenomenological input. I will talk about it more later. But there's one more component which was crucial in our model and sets it apart from other early dark energy models, and this is exactly this trigger. And the trigger is well, as I said, it's subdominant, but still very important, because the trigger seeds the perturbations in this decaying new early dark energy fluid. So once the fluid decays, it supports its own perturbations, but you have to initialize them somehow at this surface of the phase transition. And that is achieved in terms of the trigger, because the trigger itself has perturbations, adiabatic perturbations. And the way to think about it is that the phase transition is not triggered everywhere at the same time, because if the trigger reaches its threshold value a little earlier at this point in space, then the NEDE fluid starts to decay a little earlier here, and you get an underdensity at that point compared to another point. And this translates into initial perturbations in this fluid, and you can work it out on the level of the cosmological perturbation theory by doing what is called an Israel matching across the transition surface. And that is what we implemented in our Boltzmann code trigger class, which is publicly available if you're interested in testing it. Okay, but now, as I said, we are interested, of course, in establishing the dictionary between the microscopic model and this fluid model. And on the phenomenological side, we have three main parameters, which is the fraction of new early dark energy at the time of the phase transition, so typically around 10%. There's the decay time itself, redshift around 3 to 5,000, and we have the equation of state. In terms of FNEDE and Z star, we can write down these relations that relate these parameters to the masses of these two scalar fields. So we have the heavy field set by the EV scale and the ultralight field. And these are the dimensionless parameters that show up in the potential lambda and alpha. And as I said, for now, the equation of state parameter we treat phenomenologically and as a constant. And the reason for that is that, of course, in general, it's going to have a time dependence. But the point is that if it starts out as a fairly stiff fluid that decays quickly, especially given the fact that we are entering matter domination, it means that observables are not really sensitive to the subsequent time evolution. At least that's the initial simplifying assumption we make. And such a model, a three-parameter model, you can test against data. And here I'm citing from a work we did earlier this year together with the cosmology group in Aarhus. And this is the upshot of our findings. So you can reduce the Hubble tension to the 2.1 sigma level, and you get a Gaussian evidence for the model around 2 sigma if you don't include shoes. So essentially, CMB data alone gives you some preference for the model. But of course, once you include the shoes prior, the evidence goes up significantly, and you are justified to do that because you bring the tension down to the 2 sigma level. And this particular work used a profile likelihood approach, which avoids problem with prior volume effects, which you have often with Bayesian analyses in this case. So that looked promising. But let's spend a little bit of time understanding how this model actually works and why it does what it does. And first of all, of course, there's a primary mechanism at play, which is exactly what I explained before. There's the energy injection that lowers the sound horizon, which in turn needs to be compensated by increasing H0. And this is what you see in this panel. So lambda CDM is in green and clearly discrepant with the Schuh's value. But then you introduce this approximate degeneracy in this H0 RS plane, which is then can be broken by including the Schuh's prior, which gives you this red contour. And the picture, of course, is that what we actually measure is not the sound horizon itself, but its angular scale. So shortening the sound horizon can be compensated by reducing the distance to the surface of Lahr scattering, which is exactly achieved if we raise H0 in simple terms, because the universe is less old and light had less time to travel, so it just didn't travel as far. So this means that we also shorten this length scales and leave the angle in the end untouched. But this is only the primary mechanism. There are also secondary mechanisms. So first of all, and this also holds quite in general, if you are going to increase also the dark matter density, and you are going to do so by quite a lot. So if you look at this contour, you see that you increase it compared to lambda CDM by more than 10%. And that is quite remarkable, because normally you would say that, well, if lambda CDM parameters are constrained at the percent level, so you cannot get away by increasing omega CDM by 10%. It just doesn't work. And so you have to ask yourself, how do these models get away with increasing omega CDM by that much? And the answer is that there's a compensating mechanism at play. And this has been pointed out nicely in a paper by Van Hu and collaborators already a couple of years ago. And the reason is that you have these dark sector acoustic oscillations. So as I said, also in the new early dark energy models, you have the perturbations that are seeded by the trigger in the decaying fluid. And these perturbations are, of course, an oscillating system that provides positive pressure that leads to a quicker decay of the gravitational potential, and that counteracts the more dark matter you have in the system that tends to clump things and increase the gravitational potentials. And for example, on the level of the matter power spectrum, you can work out how these compensations play out. But of course, this compensation is not perfect, and you have small residual effects, especially on small scales, which leads to the fact that these models tend to increase the SA tension. So you typically go up, I mean, not by much, but still you go up from maybe 2.5 to 2.8 sigma, also depending a little bit on what data sets you look at. Okay, but this was one secondary mechanism. There is another one, and it has to do with the spectral tilt and diffusion damping, which I mentioned before. So you can write down, I mean, the fact that the CMB power spectrum falls off like an exponential, of course, is related to the diffusion silk damping we have. And this is controlled by the diffusion scale, which I call RD, or better to say the ratio of RD and the ratio of the sound horizon. But the point I want to make here is that you can, on very general grounds, you can relate the change in this ratio that controls the damping to the change in the sound horizon. And you find that whenever you shorten the sound horizon, you are going to increase the damping. And that holds, again, in very general terms, and it is the reason why dark radiation in its simplest form has problems. But the nice thing about these early dark energy type models is that they bring more freedom to compensate for that. So here you can increase the spectral tilt to counter that enhanced diffusion damping. And what you indeed observe is that the primordial spectral tilt is increased quite a lot. It even becomes 1 sigma compatible with the scale invariant spectrum. And of course, this is interesting from inflationary model building perspective. So if these these models should turn out to be the actual solution to the Hubble tension and all of that, then this is also going to have quite important consequences for inflation. And in particular, models we have already ruled out might come back to life, like a simple curvature model. Okay. So but how does this model compare to other early time models? And the point I want to make with this slide is that this is sort of a very fast moving field currently. So this was what was happening 2 years ago. There was this nice paper called the H0 Olympics that compared different models, early time models. And in particular, they also compared the original early dark energy model, which is typically called AXI-EDE, and the new early dark energy model. And both models did fairly well. They won the silver medal, which we were, of course, very, very happy about. And both brought the tension down to the 2 sigma level. I mean, new early dark energy to the 2 sigma level, and early dark energy even a little lower to 1.6 sigma. So at the time, you could ask, okay, how can we kind of distinguish between these models? After all, they have different microphysics, so can data tell us what's going on? And at the time, you could look at the power spectrum, CMB power spectra, and you would see, and this holds in general, that there are differences between models. So here I show the temperature residuals. NEDE is the red curve, and AXI-EDE is the purple curve, and you clearly see a difference on small angular scales. And you find that NEDE gives you less power here. And of course, the problem there is that the error bars in that regime are also fairly large. So data, this is plunked. 2018 data hadn't been constraining enough to really tell these models clearly apart. But what is exciting about this whole field, I think, is that this data is getting more constraining. So we have additional ground-based high-L CMB data from experiments like ACT and SPT, but also Planck data had a new release, this N-pipe data. My understanding is it's a reprocessing of the old Planck data, which brings down the error bars, in particular in this high-L region. And only a couple of weeks ago, there was a paper by Evstasiou and collaborators showing that actually including this new N-pipe data, AXI-EDE is obstructed as a solution to the Hubble tension. So the residual tension to the model is 3.7 sigma. And this, of course, means that data slowly gets to a point where it's getting a grip on, I mean, CMB data, where it's getting a grip on these models. And currently, we are also testing cold new early dark energy with N-pipe and Pantheon Plus data, and we will see how the model is doing. But I think the exciting message here is that we are getting to a point where we constrain these phenomenological models, which again is interesting for this whole model building perspective, because then you can also learn about what microscopic features work in the end or don't work. Okay. So finally, I want to exemplify how useful it is to have such a microscopic framework, because as I argued a lot now, is it compels us to introduce this trigger component to make things happen quickly. But at some point, we ask ourselves, does this trigger maybe have some additional signature? And so far, we always assumed the trigger to be highly subdominant. We only needed to kickstart this phase transition. It still plays a role in terms of the perturbations, as I said, but not on background level. But there is a kind of natural application of the trigger as a type of dark matter, fuzzy dark matter. And that idea actually is not new. So a paper by Alali and collaborators in 2021 looked at the possibility of combining NEDE with an ultralight scalar to address the Hubble and the S8 tension at the same time. And they argued that you could do it. But we ask ourselves, why introducing an additional scalar field if we already have the trigger, which we had to introduce for different reasons? So we looked at that possibility. In that case, of course, things become more constrained, as the mass of the trigger is already constrained quite a lot by the fact that we want to trigger the phase transition at the right time. But the point about this trigger is that it's an ultralight scalar field that eventually oscillates around the minimum of its potential. And these oscillations at background level behave like dark matter. But there are differences arising on perturbation level. So first, you can control the amount of dark matter you get from this ultralight scalar field in terms of its initial field value, and you can also relate it then to the time of the phase transition and the fraction of new early dark energy we have. But then the interesting thing is that you compare to cold dark matter is that you have a suppression of the matter power spectrum below the gene scale, because modes below the gene scale get oscillatory. So you create a pressure that acts against gravitational collapse. And this is what you observe. So the plot I show you here compares the NEDE model where the trigger is highly subdominant. So that's the reference line here in black. With the NEDE model where we allow the trigger abundance to be free. And the way we do it is we vary the initial field value of this trigger and make it large enough. So slightly, it's getting close to the Planck scale, but it's still sub-Planckian, like 0.1 in Planck. And then you get a small amount of this dark matter. It's not much. It's 0.6% of the energy budget, like 3% of dark matter roughly. But that gives you quite a lot suppression already of the matter power spectrum on scales relevant for S8. And so what I show you here is these two dashed dotted vertical lines are the region in the matter power spectrum where the sigma 8 integral picks up most of its value, like 90% of its value. And this is also where we suppress the matter power spectrum and then turns around again. And I think I didn't say it correctly, we compare with lambda CDM here. So the black line is lambda CDM, and the previous, the early dark energy model without this trigger dark matter corresponds to this dotted line. And indeed, you see that you have an enhanced power spectrum on small scales compared to lambda CDM, which exactly leads to that increase in S8 and the worsening of the S8 tension. But now we can suppress it. Okay, and if you use that model, it becomes a 4-parameter model, because now you have FNEDE, you have the decay time, you have the equation of state, and you have the trigger abundance today, because it's no longer subdominant. You can, in other words, we think about it as relaxing a prior on omega 5. What you find if you do a data analysis, so we looked at Planck 2018, BAO and Pantheon data, that both tensions are reduced below the 2 sigma level. If you're this corresponds to this plot where we only look at the base data sets. This then allows you to combine with the Schuh's prior, and you get a quite sizable chi-squared improvement. But what is important is, because sometimes people are worried that once we include Schuh's, we pay a high price in terms of the CMB fit. And interestingly, this is not the case. Even the fit, the chi-squared fit to CMB improves, not by much, but slightly so. And of course, the selling point here is that we didn't need to postulate no new physics at fundamental level. It's true that the phenomenological model comes with one more parameter, but at the fundamental level, we already had introduced the trigger field for very different reasons, because we needed that fast phase transition. Yeah, so let me provide a summary of my talk. So I think the H0 and S8 tensions are exciting opportunities to probe the dark sector. The early dark energy models look promising from a phenomenological perspective, but they should also be understood as an invitation to look for models that are more motivated from a particle physics perspective. NEDE is the idea of having a fast triggered phase transition in the dark sector around the EV scale. I consider it, and I try to make the point here really as a theoretical playground, a little bit similar to inflation. So also there you can think about many models that achieve the same. In particular, we looked at one implementation, which is called new early dark energy. It brings the Hubble tension and S8 tension down to 2 sigma if we take the trigger field seriously as an additional dark matter component. But I mean, I also want to stress that there's a lot more work to be done, further theoretical work. So we want to relate the microscopic parameters to the fluid parameters, which makes the model more predictive, of course. Embed the model in an axion system because you have these very small mass scales, like 10 to the minus 27. So you have to worry about how to protect them against loop corrections. It's always difficult to have ultralight masses in field theory. And one idea to achieve that is to look at axions where the small masses are protected by probe shift symmetries, because then you have an enhanced symmetry when you send the mass to 0. But also further phenomenological work is required. We want to study more general fluids, where we free up different fluid parameters even more, like allow for a time dependence, say. We want to study other anomalies and see if the model has to say something about them. And of course, keep testing, and that's currently, of course, an exciting part. Keep testing our phenomenological model against additional data, in particular CMB data, which right now seems to be the most constraining one. But there's also more going on, and I did not have time to talk about that, but you can ask me, of course. In principle, you create gravitational waves in such a phase transition, so you can ask if there's a possibility of observing them. We introduced an additional scalar field as the trigger, but you could also use a different trigger. You could think about using a temperature in the dark sector. Right now, everything is at 0 temperature in the dark sector, but there could be a non-vanishing temperature, some thermal plasma. And then you are more like the electroweak phase transition, where these thermal corrections subside as the universe cools, and then the tunneling is triggered. And that we worked out actually in the context of hot NEDE. We just haven't investigated the model phenomenologically as much as we did cold NEDE. But hot NEDE is also particularly nice from a particle physics perspective, because then you can ask, well, very, very much like the electroweak phase transition gave mass to the charged leptons, you can ask if the hot NEDE phase transition could have created the masses, the neutrino masses, and use that to address the coincidence problem you have in these models, because then they become more economical. It's not just about the Hubble tension, it's also about the neutrino masses, if you get lucky enough. Let me stop here, and thanks a lot for your attention. Thanks.
Thank you so much. Thank you. A very nice talk. Do you have any questions? Erwin?
Hey, Florian. Thanks for a nice talk. Suppose you changed weak lensing with CMB lensing, like take ACT. So what ACT are finding is more or less that basically they recover a Planck type value for S8, but CMB lensing is sensitive to higher redshifts and let's say larger scales than say weak lensing. So how would that impact your H0 if you switched out, weak lensing with CMB lensing data?
Okay. I mean, we are already using CMB lensing data in our data fit. And I mean, I'm not entirely sure if I fully understand, but if I go back to this plot, let me quickly jump
Then
back.
it's just removing weak lensing. If you're already using CMB lensing, then it's fine, right? So
yeah. So in this plot, for example, we are not using any weak lensing constraint. This is only using CMB lensing. Yeah.
Okay, interesting.
Okay, thank you. And Leandros?
Okay, thank you for the very clear talk. My question is, what about you talked about this merging of these domain walls of the bubbles before recombination, and they left out some noise, as you showed. I wonder, doesn't this noise have some effect on the CMB spectrum? Wouldn't be some signature of this there?
Yeah. Very good.
What kind of constraints do you get from that?
Yeah, very good question. So indeed, yes. I mean, these bubbles, when they collide, they create a lot of noise, but on a very characteristic scale, and that's the important part. So you get a power spectrum for that noise, and in principle, it sources isocurvature perturbations. You could be sensitive to in the CMB, and it indeed creates a constraint, and this is, or a bound, and this is this bound I showed you here, which tells you that the percolation time has to be very short, and the reason being that a short percolation time prevents bubbles from growing too big. They stay can stay microscopically small. So yes, you create that noise, but you're not sensitive necessarily to that noise in the CMB if it remains on shorter scales. That's the answer.
Okay, and I have another question. What prevents the model from going down to zero, taking the tension down to 0 sigma? For example, we just change the sound horizon, so one would expect you can make it any scale you want, so you immediately reduce the tension to 0. What is the feature of the model that doesn't allow it to go down all the way down where it should be?
Yeah. I mean, the thing is, I mean, these mechanisms I showed here, I mean, these are approximate degeneracy. I mean, of course, at the background level, you would ask, I mean, you could push that as far as you want, but then you have these secondary problems. So you're also changing other things. You're changing the amount of cold dark matter in the model. So you are going to change the matter power spectrum. And there it's harder to have this compensating effect because things happen at perturbation level now as they are compensated. So you can compensate it to some extent by having these dark sector acoustic oscillations, but not entirely. And that I think is the reason why you cannot push these models arbitrarily far. You pay a price at some point, and you see it here with the SA tension, but you also see it with the CMB damping. I mean, again, this is increasing NS is not perfectly compensating that. It's always approximately.
So this is not a general problem of the early time models. It's the models that we know so far have this problem that cannot go all the way. In principle,
I mean, in principle,
there could be some early time model which completely would fully resolve the take it down to zero tension.
Yeah, I mean, in the extremist case, you could think, but of course, it becomes you end up probably introducing a lot of parameters, but in the extremist case, you could construct a very particular primordial spectrum that is designed in such a way to cancel out these effects and make it work. I mean, that would be an extreme way of doing it, but yeah, there's a lot of model dependence in that game here at the level of these secondary mechanisms. I agree to that.
Okay, thank you.
Thank you. Simone?
Hi, hello.
Hi.
Hi, Florian. Thank you very much for your great talk. Maybe I missed this point, but I would like to know what is the main difference between this trigger field and the ultralight scalar that you mentioned on the Alali.
Yeah. I mean, in principle, there is no fundamental difference. Both are ultralight scalar fields, but this ultralight scalar field introduced by these authors was in addition to the model. So So they took our NEDE code trigger class, which has this trigger, and then they added, in addition to that, another scalar field, and they could vary the mass of that scalar field freely. We said, let's take the trigger we already have playing the role of that ultralight scalar field. But then you end up with a more constrained scenario, because then we already know what the mass of that field is, 10 to the minus 27 electron volts roughly. So that is the it's we are looking at a more constrained version of what they did. I mean, that's maybe a way of putting it.
Okay, thank you. And maybe a second question about you showed in this slide where you put a dictionary between the microscopic and phenomenology.
Yeah.
And I'd like to know, how do you set these mass scales? What is I don't know, maybe.
Yeah, where these scales come from, you mean?
Yeah,
or yeah. I mean, okay. I mean, you can understand them. The order of magnitude you can understand directly, because well, we want a sizable fraction of FNEDE of order 10%. That is what phenomenology tells us.
Okay.
But so by that I mean that NEDE, the energy density should be of 10% of the energy density at that time. And then we just know, I mean, around matter radiation equality, the cosmic fluid is set by the EV scale, the energy density. So this explains why you get the EV scale. But of course, to get the precise formula, what you do is you look at the potential, you work out the difference between false and true minimum, which you can then relate to this FNEDE parameter, because this is exactly the jump the field does and the energy that is released.
Okay, thank you very much.
Leandros?
Thank you. I just wanted to ask one more question. What are the advantages of or comparison of near dark energy compared to early dark energy? We saw in the comparison of the data where you saw that there is slightly less decrease of chi-square for net compared to early dark energy. Is there any advantage? Okay, this is maybe a small problem, but that's not really an issue. Of course, the mechanism is different. It's clear that there is a clear motivation for putting new energy because you have a different mechanism. But as far as the phenomenology is concerned, is there any advantage to this mechanism compared to the early dark energy?
Yeah, I would say right now the main advantage is that we are, so first of all, we are a little less sensitive than old early dark energy to the S8 issue, which overall we get a little less power on small scales. That is just something that comes out of the simulation. So that is, you could consider a slight advantage. Then of course we have this whole trigger story, which then really also allows us to address both tensions at the same time. That's another one. And then of course, I mean, both models are doing similarly well. And if you look now at different data set combinations, sometimes NED is a little bit ahead, sometimes early dark energy. I mean, this is now a matter of time to work out and additional data to work out which model really works better phenomenologically. And I already tried to make that point here that I mean, with this N-pipe data, this could be, I mean, we are currently working on it, but this might be additional data which more clearly starts to discriminate between those models. But by the way, also SPT and ACT data are already acting differently. So I think it's right now, I would say from a purely phenomenological perspective, it's also very useful to have two different models to kind of test them against each other and learn what in the end is like, what features are like by data.
Okay, thank you.
Sorry, Florian, if I could just on that point. So I would expect your model to work better with S8 tension than AXI-ADE, because basically what we see from weak lensing versus CMB lensing through ACT is it's either redshift or scale. That's the problem. And it's a problem in the late universe. S8 tension is
Yes, absolutely.
So your model will do better. Should get closer to the weak lensing constraints
Yeah, and it does. Yeah, I agree. Yeah, because we have this late time component in the model. We have this the trigger field acting as dark matter. I mean, yeah, that is a very, very unique feature.
Okay. What about JWST telescope? I mean, you have some indications for early, stronger early time structure formation. Can this be accommodated also?
Also, the age of the universe, Leandros.
Age of the universe. Yeah. Well, yeah. I don't have an answer to that yet. Yeah, we have to see. I mean, what I should say is, I mean, the code is publicly available, and we also want to invite people to do these tests and look at the model. I mean, absolutely, yeah.
Okay.
So new early dark energy is better than EDE.
Well,
I think it's safe to say it, Florian.
Okay, yeah, well, I don't know. Yeah.
I don't think it's too much of a stretch. I think you can probably say this.
I'm not going to contradict you on that.
So let's thank Florian again. Thank you.